So we have several options in how we can get work done away from the main thread. A pattern for performing long-running tasks without blocking the main thread is callbacks. By using callbacks, you can start long-running tasks on a background thread. When the task completes, the callback, supplied as an argument, is called to inform you of the result on the main thread. Callbacks are a great pattern. However, they have a few drawbacks. Code that heavily uses callbacks can become hard to read and harder to reason about. Because while the code looks sequential, the callback code will run at some asynchronous time in the future. In addition, callbacks don't allow the use of some language features, such as exceptions. In Kotlin, we have coroutines to handle long-running tasks elegantly and efficiently. Kotlin coroutines let you convert callback-based code to sequential code. Code written sequentially is typically easier to read and can even use language features such as exceptions. But wait, callbacks can use exceptions. Well, there is no way to signal an error from a long-running task with exceptions when coding in the callback style, as flow control has already left the functions that registered the callback. Because the callback is not typically called by the application code. Callbacks need to pass errors via another exception handler, sometimes called an airbag, or a result object which can be success or failure. So the ability that coroutines can signal errors with exceptions is very helpful and, once more, simplifies the code. In the end, coroutines and callback do exactly the same thing. Wait until a result is available from a long-running task and continue execution. However, in code, they look very different. So, coroutines in Kotlin have a few characteristics. They are asynchronous, non-blocking, and use suspend functions to make asynchronous code sequential. What does that mean? Asynchronous means that the coroutine runs independently from the main execution steps of your program. This could be in parallel, on a separate processor, but it could also be that while the rest of the app is, for example, waiting for input, we sneak in a bit of processing. One of the important aspects of async is that we cannot expect the result is available to us until we explicitly wait for it. For example, let's say you have a question that requires some research, and you ask a colleague to find you the answer. They go off and work on it, which is asynchronously and on a separate thread. Unless you wait for the answer, you can continue to do other work that does not depend on their answer, until they come back and tell you what the answer is. Non-blocking means that we are not blocking the main or UI thread. So users will always have the smoothest possible experience, because the UI interaction will always have priority. Because our coroutine code is compiled from sequential code, we don't need to specify callbacks. And for coroutines, the compiler will make sure the results of the coroutine are available before continuing or resuming. The keyword suspend is Kotlin's way of marking a function or function type available to coroutines. When a coroutine calls a function marked with suspend, instead of blocking until that function returns like a normal function call, it suspends execution until the result is ready. Then it resumes where it left off with the result. Now, while it's suspended, waiting for a result, it unblocks the thread that it's running on, so other functions or coroutines can run. So the difference between blocking and suspending is that if a thread is blocked, no other work happens. If the thread is suspended, other work happens until the result is available. Be aware that the suspend keyword does not specify the thread code runs on. Suspend functions may run on a background thread or the main thread. Now, To use coroutines in Kotlin, you need the following pieces: a job, a dispatcher, and a scope. Basically, a job is anything that can be cancelled. All coroutines have a job, and you can use it to cancel the coroutine. Jobs can be arranged into parent-child hierarchies so that cancellation of a parent leads to an immediate cancellation of all its children, which is a lot more convenient than if we had to do this manually for each coroutine. The dispatcher sends off coroutines to run on various threads. For example, dispatcher.main will run tasks on the main thread, and dispatcher.io is for offloading blocking I/O tasks to a shared pool of threads. The scope combines information, including a job and dispatcher, to define the context in which the coroutine runs. Scopes keep track of coroutines. When you launch a coroutine, it's in scope, which means that you've said which scope will keep track of the coroutine. Now, if you want a more in-depth technical explanation, I'm linking a great code lab written by one of our coroutine experts and fellow instructors, Sean, and also the official documentation. So let's use some coroutines and dive into the details of how to use them in code.